Okay, we got cut off a little bit prematurely, so I was going to give you another divergence test. So we say determine the convergence or divergence of the series, and this is going to look horrendous, but it's going to go series n is equal to 1 to infinity, and you can make stuff up like, okay, so n squared minus plus 2n plus 1 divided by 3n squared plus 4n or something like that. So here's the thing. The idea is, if I look at this thing, I'm looking at that going, you know, if n goes to infinity, we're going to go to, the a sub n is going to go to 1/3. I can see that. So nevertheless, I'm going to say, I'm going to run the divergence test. Okay, and I'm going to take the limit as n goes to infinity of a sub n, which is the lim as n goes to infinity of n squared plus 2n plus 1. That's how you make it official. 3n squared plus 4n. And all you have to do is say, you know what the limit is there? It's like the lim as n goes to infinity of n squared over 3n squared. It's really equal to 1/3. And guess what? That's not 0. So that implies the series, I don't have room to write it here, series diverges. Okay, so this is like, this series here that I just messed around with is like a series that adds terms that are slowly becoming more and more like 1/3. Here's the thing to realize. If the series don't go to 0, if the terms don't go to 0, you got divergence. That's our first test right now. In fact, after this lecture, that's still going to be our only test. But we're going to learn some more stuff. Now, this is a cool one, the harmonic series. Guess what? It actually diverges. Look at it. We have series 1 over n. n is 1 to infinity. So the first term is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus forever. Now here's the thing. If I ran the divergence test on this guy, watch what happens. I go lim as n goes to infinity of a sub n. That's lim as n, you can skip that first part, and n goes to infinity 1 over n. And you know where that goes. As n goes to infinity, got 1 over infinity, is 0. You know what a lot of students want to do? They want to say, implies the series converges. Yay! Because it went to 0. And I go like this. No, it doesn't. It doesn't imply that at all. I'm sorry to say. So, surprise in the land of it. Here's how I show this. It's a little ahead of the game. The next section talks about something called the integral test. But I'm going to run it anyway. This is what I always do in lectures, is I look at the function 1, or the series, a sub n equal a sub n. Oh, I'm sorry. I look at the series 1 over n. n is 1 to infinity. And then what I do is I look at the sequence a sub n is 1 over n. And then I look at the function f of x is 1 over x. Why are you going far afield, Weber? Well, this is where we start getting a little deeper in this stuff, okay? Remember that thing where I wrote the curve down? I'm going to do it again. This curve, 1 over x does its thing. Y equals 1 over x. There's another piece here. You know what? I don't care about it. Why? Because n is only going from 1 to infinity. So what I'm doing is I'm showing you where this sequence is, okay? 1 gives you 1, 2 gives you 1/2, 3 gives you 1/3, and so on, okay? The ordered pairs would be n and 1 over n, and we've seen it before in algebra classes. 1, 1 over 1, 2, 1/2. You know what? You see it up here, don't you? Those are the terms. Now here's the funny thing about this, okay? What we can do is compare these areas of rectangles. This is actually the gist of the integral test in section 3. But the areas of the rectangles that I'm drawing in right now, okay, are actually larger than the area under the curve. Would you not agree? The area under the curve here is here, right? All this. I'm trying to be a Rembrandt here. So the area under the curve looks like that. So what I'm saying is the area of all the rectangles is greater than the area under the curve. Now notice, we're going to let this sucker go all the way to infinity. That's an improper integral if we did that. What if I were to say to you that the area under the curve is infinite? What would that say about the area of the rectangles that are bigger than infinite? It would also be infinite, and that's how I go about this. I simply go, let's look at the integral from 1 to infinity, 1 over x dx. That's the natural log of x from 1 to infinity, which is the natural log of infinity, if you will, minus the natural log of 1. Well, we know that this guy, of course, is 0, but that's not the important part. The natural log goes to, I know you don't believe me, but it does. It goes to infinity. This guy is infinite. It's unbounded. It's slow, and I spend more time with it in class, but it is definitely unbounded. The curve of natural log is real slow, but he does go off to infinity. So what does that say about our guy? Well, that says, let me cruise down here if we got room. That says that, the series 1 over n from n equals 1 to infinity is greater than infinity, if you will, implies that the series n is 1 to infinity, 1 over n is equal to 1 plus a half plus a third plus etc. It diverges. Now note, that was a lot of work. You can pause it and look and rewind it. That's a lot coming at you. But here's what I'm telling you. We ran the divergence test and we got 0. Oh, we'd like to think it converges because it went to 0, not non-zero. But it actually diverges. So there's no way to tell whether it's going to converge or diverge or not. And that's the divergence test, okay? I might halt this video and go to the last two types of series, and I think I will. So that's interesting, though, that what you've got here is, and I can go on and on about this thing. It's pretty cool. When we get to the next section, we'll talk about the integral test. Yeah, but what's the takeaway here? Well, the takeaway is the divergence test. The divergence test, we did it on the last tape, and then it got crazy, and then on this video we went a little deeper into it. And what we're showing you is that, hey, if the terms go to 0, as I've been saying, the thing we don't know. But if it doesn't go to 0, we've got divergence. So that's all the divergence test can tell you. Plus, we introduced an interesting series to you called the harmonic series. All right, let's call a halt to this one and do one more in this section.